Okay, so we have studied weak acid problems, weak base problems, acidic salt problems, and basic salt problems. Now what we're going to do is kind of put some of those ideas together in something called the common ion effect. What a scientist, a person, anybody who's studying chemistry can do is they can take a weak acid solution or a weak base solution, either one, and they can add to it a salt. If they add to it an acidic or a basic salt, it will obviously affect the equilibrium position of that weak acid or that weak base. Because instead of starting with no product, you are actually going to have some ion there before you begin. Hence the reason why this is called the common ion effect. Now, one thing you're going to notice is that no matter what weak acid or weak base it is that we are using, the salt will have an ion in common. So for example, if we're using acetic acid, your salt would have to be some sort of acetate salt, some sort of salt that also has C2H3O2 in it. And you're going to notice that in the example problems that we are going to do. So let's go ahead to the first one so you can see how this will work. It looks similar to the problems we've been doing. You notice they give you the pH of the acid solution itself. And then they want to know what the pH will be of the solution if it is 0.25 molar acetic acid. So that's your concentration of your acetic acid, and obviously that is a weak acid. And then they tell you you're adding 0.1 molar sodium acetate. You see it starts with sodium. That means it's a metal. That means the substance is a salt. So we have to decide what kind of salt it is. Well, actually, to be honest with you, you don't have to decide what type of salt it is because the problems have to be a certain way. But if we were discussing that, we would say that sodium acetate would be a basic salt because sodium comes from sodium hydroxide and acetate comes from HC2H3O2, which is a weak acid. But to be honest, we don't have to worry about it in these problems. Now, here is how this is going to work. In your table, okay, when you have a weak acid with a salt or a weak base with a salt, your table equation is still the equation for the weak acid or the weak base, not the salt. So we'll start by writing our acetic acid, which is HC2H3O2, into our table. Do our double-sided arrow, just like you would if this was only acetic acid. Okay, so the salt does not affect the equation that gets written on the table. If this was a problem of salt all by itself, we would put the equation in the table. But because this is a weak acid with a salt being added, the primary part is the acetic acid solution. So we're going to write that equation in there. Now, what else we have to do before we can go any further, just like we did with our salt problems, is we are going to write what this salt does when it's put into this aqueous solution. We know it's going to break up, single-sided arrow, into Na plus and C2H3O2 minus. And just like with our salts, we need to figure out what the concentration is of the salt itself. Excuse me. That is funny. Since last time I did the same thing. Anyway, so the concentration here is 0.1 molar for the NaC2H3O2. We don't care about that. We care about this ion right here. We care about the ion that is common to both the salt and the weak acid. Sorry, and the weak acid. So the ratio from here to here is 1 to 1. So this is also going to be 0.1 molar. Okay? So we have to do that off onto the side. So again, if you have a solution with a weak acid and a salt, write the weak acid equation into the table, take the salt, break it up, figure out the concentration of the ion that is common to both of them. And again, acetate is the common part to both of them. All right, now for your table, here's where it'll be a little bit different. Similar, but different. We are going to start over here with our acid and write in our concentration of our acid just like we would normally. Now, normally, if this was only a weak acid solution, we would put a 0 here and a 0 here. However, we do not have 0 ion this time. We do have 0 in the H+, so this 0 is right. But this ion right here has a starting value this time. Instead of being none, we've put the salt in, and the salt has given it an initial concentration of 0.1. So we do not have a second zero over there. So that is where these problems are different. And again, this is called common ion effect because you had your weak acid, but instead of starting with nothing on the product side, we are starting with one of the ions already there, which obviously is going to affect the equilibrium, how the equilibrium will get established. Now, from this point forward, the problem is the same. So we put our x's, bring our coefficients down. Excuse me. I'm going to make this side negative, this side positive. So I'm going to have 0.25 minus x. I'm going to have x and then 0.1 plus x. Now they want us to calculate the pH of this solution that has both of these in it. To do pH, we know we need the H plus concentration. So I'm looking to find this value right here. So we're going to use the Ka. This is an acid problem. So Ka is the appropriate equilibrium to be using. So Ka is H plus times C2H3O2 minus all over HC2H3O2. I know my Ka was given in the problem as 1.8 times 10 to the negative fifth, which means we can use our trick. So H plus is represented by X. C2H3O2 minus is represented by 0.1 plus X. And then on the bottom, HC2H3O2 is 0.25 minus X. Now our trick tells us that we can get rid of anywhere where X is being added or subtracted. So I'm going to get rid of it here and here. Don't get rid of the actual 0.1 and 0.25, but you can get rid of the rest. All right, so if we cross multiply and then divide over the 0.1, we end up with an X value of 4.5 times 10 to the negative fifth. That X value is what we need to plug in here because that one is represented just by X. So 4.5 times 10 to the negative fifth molar is our concentration of our H plus. I'm not even going to plug it in on the other two because I'm not solving for either one of those. I just want pH. So the pH of this solution is going to be the negative log of the H plus. So pH is going to be equal to the negative log of 4.5 times 10 to the negative fifth. So pH is going to be equal to, when you plug that in, you get 4.3. Now, earlier in the problem, they had told us the pH, go back up here for a sec, they told us the pH of just regular old 2.5 molar acetic acid was 2.67. Notice we didn't use that number. I've put that number in the problem just so that you could see what happened. This acid started off with a pH of 2.67. We added a basic salt to it. Okay, we added a basic salt. That salt is going to introduce OH minus ions, which are going to neutralize some of the H plus ions. And when they did that, they took the pH from this 2.67 up to 4.3, which makes sense. You add something basic to something acidic, and it will become more basic. Now, it's still an acid, it's still 4.3, but it's not as acidic as it was before. Okay, so that's the way these problems will be set up. Let's go ahead and try a second one just so you can see what that'll be like. Oh, that's awkward. Sorry about that. I didn't mean for that to get slipped into the PowerPoint. Oh, he's going to hate me for that. Oh, okay, here we go. Problem. So assume you have a 0.3 molar solution of HCHO2 and I've added enough sodium formate to make the solution 0.1 molar in the salt. Now, you may look at sodium formate here and say, I don't know what formate is, but remember it has to have an ion in common. So you can see here by the HCHO2 that formate must be the CHO2 minus ion. Okay, so that's going to help you as you're doing this problem. So we have an acid, a weak acid. The basic salt has been added to the solution to make the salt 0.1 molar. Calculate the pH of this formic acid solution after adding the sodium formate. So here's our process. Start by getting your equation into your table. The equation we put in the table, because this is a combo of a weak acid and a salt, means we go back to just using the acid equation. That is the primary part of this solution. We are not ignoring the fact that we have added a salt. We are only going to represent the salt where it belongs. Okay, so now you will take your salt, sodium formate. So sodium has a +1 charge. So if you crisscross that, sodium formate is NaCHO2. Single-sided arrow gives me Na plus and CHO2 minus. The ion that is common to both is this formate ion. So that's the one we care about, the concentration. They've told us the concentration of the salt was 0.1 molar. So if the salt is 0.1 molar and the ratio is 1 to 1, then this one is also 0.1 molar, which means my starting value for this ion is 0.1 molar. Now let's go back to the weak acid. The weak acid, they told us here, was 0.3 molar. So 0.3 gets plugged in here. And we still are starting with no H+. Okay, the salt only brings in the common ion, not also the H+. So now the table is a normal table. So I'm going to do -x, plus x, counting for my coefficients. They just happen to all be 1s. 0.3 minus x, I have x, and I have 0.1 plus x. We are trying to calculate the pH, so we need to figure out H+ concentration, this guy right here. So we need to figure out what x is. Now they also have given us in the problem the Ka value. So I'm going to write Ka equals the concentration of H+ times concentration of CHO2 minus, all over the concentration of HCHO2. My Ka was 1.8 times 10 to the -4th. Okay, so we're going to use our trick on this one. We're going to call this x. This is going to be 0.1 minus x. No, we said plus x. Okay, and then over here is going to be 0.3 minus x. Now we are using our trick because we've got 10 to the -4th. So get rid of this and this. This will make the math a lot easier. Cross multiply the 0.3 and then divide over the 0.4, and you end up with an x value of 5.4 times 10 to the -4th. Now, if you used the quadratic on this, or if you graph this in your calculator, I believe you get 5.35 times 10 to the -4th, which of course is okay. If you don't use the trick and you go that way, it's totally fine. The answer actually comes out exactly the same regardless, but I just wanted to point that out. So this 5.4 times 10 to the -4th goes here. That is your value of x, and that is your concentration of H+. Now we want to calculate the pH. So pH equals the negative log of H+. So pH is going to be equal to the negative log of 5.4 times 10 to the -4th. So the pH is going to be equal to 3.3. Now, both of the examples we did involved a weak acid with a basic salt added. We will sometimes, at some point, do basic solutions with salt added, but they are not as common because basic solutions, we add acidic salts, and we already discussed in class the fact that an acidic salt is just not as commonly used because there's not that many of them out there that we can make use of. Okay, so again, just to run through it, you know you're doing this new process because you have a weak acid with a salt added. So you want to put the weak acid equation in the table. You're going to account for the salt in just the ion. So right here is where the salt gets accounted for. You're going to do that. You're going to do the rest of the problem exactly the same. So, all right. Your homework problems are on the back of your paper. I'm not sure if I have them all marked correctly. So these are the ones you need to do. You're going to do 17.15A, 17.17A, and 17.17B. And I've given you the answers here. Two of them are asking you to figure out the percent ionization, and I have that equation written on your homework sheet. It's just whatever your X is divided by the initial molarity of the acid itself. So you're going to divide that and then multiply by 100. It'll tell you how much of it actually ionized. So that's your answers to your homework problems. And then I also need you to shoot me a quick email. I want you to explain to me in the email why this is called common ion effect. If you don't know, then go back to the beginning of the video. Number 2, just let me know if you have any questions or anything like that. And then 3rd, let me know how excited you are that the AP test is coming very soon.